Hey guys, hope you all had a good weekend. Sorry I can't make it today. I'm going to be at, unfortunately, my auntie's funeral, so I'm sure you'll be having more fun than I will. Hey, so what we want to cover is section 5.2 and 5.3, which is all about series and parallel circuits. If we get time, we'll touch on 5.4, which is the harder stuff, but it's basically about applying Kirchoff's laws to series and parallel circuits. So really, if you look at Kirchoff's laws, there's the two that we talked about. First of all, number one, the fact that current doesn't get used up. So whatever current comes into a junction, comes out of a junction, you can't create or destroy charge. The law of conservation of charge. Second one is the voltage law. Essentially, it's from the law of conservation of energy this time. And whatever energy essentially you put into a circuit will be used up in the circuit by the time it gets back to the opposite pole of the whatever the power source is. So if we start with series circuits, pretty straightforward really. We've really sort of covered a bit of this before. A series circuit is a circuit where there is only, of course, one pathway that the charge can flow along. If there's a break, it'll stop working. That's called an open circuit, which I think a lot of you already try that writing again. That's better. Open circuit, which a lot of you know all about. So a couple of key points. First of all, with series circuits, if you want to know the equivalent resistance, you just add them all up. Really straightforward. So the several individual resistors connected in series in a circuit could be replaced by one whose resistance equal to the sum of the individual resistors. So key point there is that the total resistance is you just R1 plus R2 plus R3, add them all up as long as they're in series. And if we go to the next worksheet there, we've done this one in class. You'll see like question 2 is really kind of what it's all about. It sort of reinforces some of that. The next worksheet that we had, which I think was on the back of that first unit one, it asks you just to sort of recognize what's in series and what's in parallel. So for example, like those two are in series, and of course the ones in parallel, what have we got? That one, it's an interesting one. That one's in parallel. That one's in parallel. That one's, you got two circuits. All right, so you should be able to work your way through that one. We'll keep going with series circuits, and when we look at this diagram kind of up the top here, get rid of that, that's better. The diagram at the top here, page 31. Page 31. The diagram up the top there is kind of key for our understanding. This time here, obviously, like it says, the current through each resistor is equal because there's only that one path. So whatever current we've got, that one point will be the same as the other point. It doesn't matter where we chuck an ammeter, it'll read the same. So we've talked about adding the resistance. We've talked about the current being equal anywhere on the circuit. And lastly, of course, the voltage, which is a direct application of Kirchoff's laws. The voltage across the terminals of, well, in this case, a battery or energy source, of EMF, remember, electromotive force, the force that motivates the electrons. So the voltage of the EMF is equal to the sum of the potential drops across any of the resistors. Now in this diagram, it's interesting, we actually don't have a source of voltage. So if we say that was like a what I just drew in there, let's say that was a 12-volt battery. If all these resistors were equal, you'd have 4 volts across the first one, 4 volts across the second one, and what's left? 4 volts. And the diagram that's sort of good at explaining that, I'll get to in a minute. But yeah, it's like energy in is equal to energy out, and yeah, key concept for us to understand. So like example 1, if we move on now, that's about as easy as you'll get. We'll skip that one. Example 2 is a good one to have a crack at, because it's easy, but it just takes us through those key concepts. So first one is the sum of the resistance. What do we got? 10, 5 plus 10 plus 7.5, 22.5 kilo ohms. Don't forget that. Always look at the diagram. Tests and exams, yeah, that'll get you if you're not watching. Hence the current through each resistor. Well, the current through, there we go, the current through each resistor is going to be the same, which is your total current. Now, I is equal to V on R. Which V and which R? If you want to know the total current, a good way to think of it is EMF over your total resistance. In this case, it's 45 joules per coulomb, and our total resistance was 22.5 by 10 to the 3. So 45 over 2.5 by 10 to the 3. I got 1/500th. What do we got? 2 by 10 to the negative 3. That makes sense. I shouldn't need to do that, should I? 2 by 10 to the negative 3 amps. Okay, use Ohm's law to find the potential difference, potential drop across R1, R2 and R3, and compare this to the EMF supplied. Okay, so first one, the voltage across R1, V is equal to I times R. With this question, you'll hopefully get the idea that we're using Ohm's law heaps. You just got to know which V, which I, and which R to use. So the voltage drop across R1, what was the current going through? It was 2 by 10 to the negative 3, and the resistance was 5 by 10 to the 3, get rid of those, 5, 2, so it's 10 volts. Next one, pick up colour, the voltage drop across R2, same deal, I times R, which was 2 by 10 to the negative 3. In this case, it's 10 by 10 to the 3, 2 tens. Okay, so we've got 20 volts. Now, if everything goes to plan, we should get 15 volts across the last one. Change in volts across the third resistor is I times R, and same deal, 3, and the resistance in this case was 7.5 by 10 to the 3. They cancel. 2 times 7.5 is 15 volts. So our overall, our EMF was 45 volts, and 20 plus 10 plus 15 is equal to 45. So it's equal to the sum of the potential drops across each of the resistors. So to summarize, the key understanding with this one is, you'll see again and again, you just use Ohm's law, but you've got to know which V, which I, and which R to use. Cool. All right, so let's keep cracking with, here we go, let's do parallel circuits. You've got the Hewitt worksheet there to have a look at as well, which again, that'll explain it quite nicely, but we'll have a look at our notes here. What I might do is I'll stop it there and I'll start another one, and I'll do parallel circuits for the next one. Cheers.